A U-tube manometer contains two fluids with different densities as shown. The fluid positions shown in the diagram are for the case when the tube is not spinning. It is then spun around the axis shown until the liquid level in both legs are equal. Find omega. So let's take a look at this. So a U-tube manometer shown here contains two different fluids with densities as shown. So this lighter shaded fluid here has a density of 1200 kilograms per meter cube, and the darker fluid here is 1000 kilograms per meter cube. The fluid positions shown in the diagram are for the case when the tube is not spinning. So the tube is just stationary here, and so we'll notice because this fluid is a higher density, this free surface here is a little bit lower than this one. Now the only dimensions given on here are the height of the column of 1000 kilogram per meter cube fluid is 10 centimeters, and the distance between the two vertical legs here is 20 centimeters. Notice we're also given a direction of gravity aligned with the axis pointing down. So what happens now is this tube is spun around the axis shown. So notice there's an axis shown here, and there's an omega indicated down here around that axis, and it's spun until the liquid level here and the liquid level here is equal. And what we're trying to find is this omega. So that's what we're after. So the given information in this case is really the diagram that we've already been given, and we may add some supplementary information on that as we proceed through the solution. So what are we asked to find? Well, we're asked to find omega, the rotational speed required to make these levels the same. So that's what we're asked to find. The assumptions that we'll be making. Again, we'll just leave a blank list there right now, and we'll get back to adding the assumptions into that list as we make them. Our analysis. So first thing we want to do is put a coordinate system on this diagram before we get going on the analysis. And this is a rotating system, so we want to use a cylindrical coordinate system. And I want to align my z-axis with this axis of rotation. So I'm going to turn this into my z-axis, and then r is going to be the radial coordinate. And notice I'm putting z equals 0 at this liquid level, at this original liquid level. And we'll see how that plays out as we go through this solution. It doesn't really matter where we put that origin, but I'm going to put it there. It might be a little bit easier later on. So we've got our coordinate system established. Now, the whole approach to this problem is going to be to recognize that both of these tubes are open to atmosphere. So notice the tops of these tubes, they're both open to atmosphere. So this point here and that point there are always at atmospheric pressure, no matter what. So when it's stationary like this before it starts spinning, those 2 points are at atmospheric pressure. As it starts to spin and this fluid raises in this leg and drops in this leg, those 2 points are still going to be at atmospheric pressure. So what we're really doing is taking those 2 points and setting their pressure equal. So that's the premise we want to start with. So I want to label a few points here. I'm going to start over here, call that point A. This interface where it goes from the 1000 to the 1200 density fluid, I'll call point B. And then we go down through this fluid, this second free surface here, I'll call point C. And we're going to be making reference to those points throughout the solution. So down in my analysis, what I want to say is PA minus PC is equal to 0. And that's going to be true whether it's stationary, whether it's spinning, no matter what happens. Well, PA minus PC is a function of the pressure change in those two different fluids. So I'm going to break that down into PA minus PB is the first step, plus PB minus PC. So notice in this expression, these PB's cancel, negative there, positive there. So this is really just another way of saying PA minus PC, which is the same thing here. So That's equal to 0. Well, where do I get these pressure differences from? Well, from the basic hydrostatic equation. It's always our starting point. So the pressure gradient is rho times G minus A. In this particular coordinate system, our G here is equal to minus GK. Notice the Z is pointing up, so K is the unit vector in the Z direction. This G is in the minus K direction. So we'll just make a note of that down here as well. G equals minus GK. Now notice, because I pulled out the basic hydrostatic equation here, I need to say here that the fluids are in a hydrostatic state. So let's just go back to our diagram and refresh ourselves as to what that means. Certainly before this starts spinning, these fluids are just stationary in here and they're in a hydrostatic state. When we start spinning this thing around this axis, the fluids are initially going to move. That's going to go up and this is going to drop down. But eventually, for a constant value of omega, they'll steady out and the fluid will again be in a hydrostatic state. So we'll be looking at it in those two conditions, but in both of them, the fluids will be in a hydrostatic state. So we make that assumption, and that justifies using that equation. So we've got our G for our coordinate system. Now in a rotating system like this, the acceleration is equal to minus omega squared r in the r hat direction. So r hat is a unit vector in the radial direction, so that's r hat. And the acceleration of this fluid is always towards the axis of rotation, is in the minus r hat direction, and its magnitude is minus omega squared r. So that's our acceleration. So we've looked at the right-hand side of this equation. We've written G and A for our particular coordinate system for this particular problem. So what we have so far here is a pressure gradient that is equal to rho minus GK plus omega squared r hat. So notice there's two unit vectors here, so two components to the pressure gradient. Now, the dr that we want to talk about here, notice that the plane that we're looking in here is an RZ plane. So as we move in this plane, we're always going to be moving in the R or Z direction. So we define our position vector dr just as being equal to dr in the R direction plus dz in the K direction. So as we move around, either up and down or left to right in here, we're either moving in the Z direction or in the R direction. So as we move through this fluid, our dr is always going to be drr plus dzk. If we're moving up and down, this will be 0. If we're moving left and right, will be 0. But this is always going to account for any motion in the RZ plane. So that's our dr. Now, the pressure difference between any 2 points in this fluid, okay? So dP is going to be the pressure gradient, and we've got an expression for that here, dotted with dr. So remember, that's how we find a pressure change in a pressure field. You take the pressure gradient, dot it with dr. So this is just dP if we want to actually find the pressure between any 2 points. So I'll call those 2 points P1 and P2 right now. That is the integral from 1 to 2 of dP. Okay? Well, that is equal to the integral from 1 to 2 of our pressure gradient dotted with our dr. So we have an expression for those two things, so we put them in here. Integral from 1 to 2, pressure gradient is rho minus gk plus omega squared r hat, dotted with the second vector, which is dr r hat plus dz k hat. So substituting in for the pressure gradient and for dr. Next thing we do is actually take the dot product. So this dot product, so we have a density out front here, and in here we would have minus g dz, so the k component multiplied by the k component, plus r omega squared dr. So that's the r component multiplied by the r component. Now notice, that's a vector, but we've taken the dot product so the result is a scalar. There's no unit vectors in this anymore. It's just a scalar quantity, P2 minus P1. And again, this point 1 and 2 can be any 2 points in this problem as long as they're in the same fluid. So we have yet to do the integration here, but we can do that now after we've done the dot product. So this is just going to be minus rho g times z2 minus z1. And the second term is going to be plus rho omega squared over 2 times r2 squared minus r1 squared. So notice there's an r in here. So when we integrate it, it becomes r squared over 2, substituting in the limits. So this is r over 2, r2 squared minus r1 squared. So that's the pressure difference between any 2 points in this fluid. So notice there's part of this that depends on changes in z coordinates, and part of it that depends on changes in the radial coordinate. And the two of those effects together give the total change in the pressure. So now what we want to do is use the right-hand side of this and substitute it in to here and here. So we get the total pressure change going from A to C as the sum of 2 parts of that. So we go down here again and go back to PA minus PC being equal to 0. So that's going to be equal to applying this equation first of all in fluid A, and I'm going to go back and label these two fluids so I can use those labels as a subscript. This fluid here I'm going to call fluid A, and this more dense fluid here we'll call fluid B. So we'll just use those lowercase a and b to designate our two fluids. First of all, writing this equation down for PA minus PB, that'll be minus rho fluid A times G, and Z2 minus Z1. Let's take a look at that. That is, in this case, is just ZA minus ZB because we're doing A to B. So this becomes ZA minus ZB plus still density of fluid A, omega squared over 2, and this is RA squared minus RB squared. Now, take a look at that. The radial coordinate of A and B are both the same. So that just cancels out. So RA minus RB is going to be 0. Now, that's true as long as this fluid doesn't have to go down so far that this point B goes around the corner. So really, when we do that, we're assuming that this fluid A stays in the right leg. So we should put that in our assumptions list here. Fluid A stays in the right leg. And it certainly looks from this diagram that this doesn't have to go down very far to make this even. But that's an assumption we'll have to make. And by saying the fluid A stays in the right leg, the radial coordinate of point A and B are both the same, and in fact they're both 0. So that's why we were able to cross that term off. Now, we should also recognize that along the way here, we've assumed that this density is a constant, right? When we did this integration here, the density was assumed constant, and in fact G was assumed constant as well. So we've got to go back here and say rho and G constant. Now, of course, the density of the two fluids are different, but within each fluid, it's constant. So, continuing on with this, what we have down here so far is just PA minus PB, but there's a second half to this. So the second half of this, the density will be rho B times G ZB minus ZC plus density of B again, omega squared over 2 RB squared minus RC squared. Now notice in this case, RB and RC are different. So RC is over here and RB is over there. So again, we're assuming that point B stays on this side and doesn't come around here. So RC minus RB is 20 centimeters. Or another way to look at it is RB is 0 and RC is 20 centimeters. So we know what those are. So when this is spinning, ZC will equal ZA. So go back and take a look at that. That's the whole premise that this problem is done under. So the fluid position shown in the diagram of a case when it's not spinning, it is then spun around the axis until the liquid levels in both legs are equal. In other words, ZC equals ZA. So that's why down here I've said ZC equals ZA. So therefore, ZB minus ZC is equal to ZB minus ZA. Right? Because C and A are the same, so B minus C is equal to B minus A. So that's fine. So this expression, we still have 0 for the pressure here, equals minus rho A G Z ZA minus ZB minus rho B times G ZB minus ZA plus rho B omega squared over 2 RB squared minus RC squared. Now we're ready to substitute numbers into this, because if you take a look at this, the only thing we don't know in this expression is omega, the angular speed. So the angular speed is right there. We know all these densities. We know all of these elevation changes. So A minus B and B minus A, of course, are just going to be 0.1 meters and negative 0.1 meters. Just go back and take a look at the diagram, show you that. So 0.1 meters, 10 centimeters. So just a matter of substituting numbers into this. So we have 0 here. Rho A is 1,000, so minus 1,000 kilograms per meter cubed. Units go in whenever numbers go in. G is 9.81 meters per second squared. ZA minus ZB is just 0.1 meters. Minus the second term here, density of 1,200 kilograms per meter cubed. G of 9.81 meters per second squared. And ZB minus ZA is going to be negative 0.1 meters. And then the last term is the one with the angular velocity in it. So we add to this rho B divided by 2. I'm just going to divide the density by 2 to take this into account. So that'll be 600 kilograms per meter cubed. Omega squared, so that's what we're after, times RB squared. Well, RB is 0, it's on the axis, and RC is 0.2 meters, and that's squared. So that will be meters squared, the R squared. So we solve for this omega, and you solve for that omega, the number you get is 2.859, and of course that will be in radians per second. And if we divide that by 2 pi, we would get revolutions per second, and multiply by 60, we get 27.3 revolutions per minute. So omega is 27.3 RPM.